Sounds good. Welcome back. So I think we have 20 minutes left in my session. We looked at the memory. Now we will look at the course. And it's linked in a couple of places, but again, just like later in a week or two, if you want to find this, now I will find this other. And it is under jobs. And now I will go for the how to choose the number of cores. I'll go here. And again, there is motivation why, but we talked about it already. Why it matters also for you, not only for the taxpayer and all the other people who want to run their jobs. There are a couple of ways to find out how many you really use. Two tools which are really nice. They are currently, there is some trouble, we are working on it. So I will not talk about the Slurm browser, I will not talk about ARM performance reports, but we will update the documentation as soon as these are back to life. One way which is really good, I use it very often, is to start your job, find out on which node or nodes is it running, go into the node and run top and have a look. We will do that. Then you get information about memory. You get also information about, like, are all the different guests sitting on one table or are they nicely distributed over the tables? And the thing that was really emphasized so often is to do the scaling study. I really want to do the scaling study now together. And we will take a code, and it's a C code, and we don't have to really understand what the code is doing. It's doing some computation, and it's also doing some communication. And it's a fantasy code that I wrote. Doesn't matter what it's doing. We can imagine that we need to use this for our research. It's a black box. And I want to know, at the example of Saga, how many cores should I run this on? So just as a preparation here, I will leave this script from before. I will maybe make a new folder just to not mix things too much here. Demo course. Let's go in. And first step I will do is I will compile this code into a binary. Copy. And I call it example.c. And this example is in C, but really doesn't matter. We could the same things you can see in Fortran and C++ and Python. Really doesn't matter. So we don't want to look at it again. I just want to compile it. For those of you who build software, one thing I like to personally do is when I compile a code, I don't just compile here in the terminal, just like that. You could. What I like to do is I like to put this in a script also, because then if I come back to it in a year, I don't have to remember how I did it. I can just look it up. So I will create a script just to compile my code. And if the compilation takes 2 hours, then you might even want to submit this as a job. Might not be a bad idea. So all this thing will do is it will translate it into a binary. We don't have to worry about the rest of the stuff. I make it executable. And I compile it. I'm still compiling here on the login node because we were told that this is okay to do. There was no Slurm involved now. I would involve Slurm here if this really took more than just a few seconds. And now I have this mystery binary, and I don't know how many cores I should use. So let's make a study on it. And I will take this example run script, copy it here. We need to adapt a little bit again, because I didn't do that. Was it 9987? And also reservation, and we don't need this. So what do I ask you for? I ask for 2 minutes. I ask for only 1 gigabyte. And I really don't know how many cores I should ask for, but I start with 8. What does this line do? This line will produce an output instead of slurm minus job number dot out. It will create an output called 008 out. This will make it easier for me to compare. So I throw all the modules out. I load only the one that I need. And this is the one that I also built the library with, or sorry, the binary with. And then I run it with srun. And srun will already know, it will understand that since I asked for 8, it will try to run it on 8. So I don't have to specify anything here. Yeah, let me also have a look. Yeah, and how do I know the number of tasks? Well, we don't know. So I start with something. Maybe I should start with 1. Here I got the script from a colleague. In the script there was an 8. So let's try with 8. But the goal of this exercise is to find out what is an optimal. So let's save, and I will submit. And it's already running, and it's running. If I wanted to, I could also SSH into the node and have a look, but maybe I'm not quick enough. I actually don't even remember exactly how long it will run. It already finished. So it took like a couple of seconds, and I have an output file here. And in the output file, what do I see? There is the information about memory that we already remember. It also tells me something about runtime. So this step took 4 seconds. I mean, there was a lot of, it did some other things, but because it needs to load the module, it needs to set up all these things, but the actual runtime was, that it spent in the binary was 4 seconds. And now, so what a scaling study is it's now to, I mean, you don't have to go by powers of 2, but that's what people often do, is to try it out now on 4 and on 2 and on 16 and on 32 and 64 and 128. And I can maybe, and what you will see here, why did I spend a lot? Oh yeah, no, that does make sense. So now we did this, 8 cores, we spent approximately 5 seconds. And what I would do now, and it maybe looks a little bit tedious, but I would actually rename this to, I would rename it to 008. And I mean, there are more elegant ways, but I would do it really pedestrian here. I would go and 4, 2, and 1, and I would just for the fun of it, I will launch all of them. Maybe we can stop here. Of course, I still need to actually adapt these run scripts. So let me go in and adapt all of them. So the 001, it should produce 001, and it should only use 1. The 2. So a little bit tedious, but not too tedious, and the benefit will be huge because I will really know. 4, 4, 8 is correct. 16, 16.
Radovan, are you going to run the same binary in the job script?
Yes. Same binary, but on different number of cores. And what was left? 32 and 64. And if I want 182, but it will actually produce the same thing as in the table. And what was it? 64. And now let me launch all of them. maybe I can show you some actually nice shell stuff. So for file in run do as batch, so loop over all the files and submit them, boom, all of them. Instead of doing this, you could of course submit them one by one. And now they are running. Some of them will finish earlier than others. Okay, some of them are already finishing. 2 more left. 1 more left. And now, let me get a nice summary. Grep is a command to take a line out of outputs. So I know that this was called binary in all these outputs. In all of these outputs, extract all the lines that contain my binary. And this is, I need to make it a bit nicer. So it's maybe a bit tiny, but of all these outputs that I did, I'm actually now mostly interested in the timing. So does that match this example? It does. On 1 core, it takes 33 seconds. On 2 cores, it's roughly halved. So it's really a good idea to go from 1 to 2. It's also a good idea to go from 2 to 4. From 4 to 8, still, time is halved, so that looks good. Okay, I ran this twice, that's why I have it twice. Then, if I compare from 8 to 16, doesn't look like really big improvement there. Doesn't really match here. The table, interesting. Okay.
Radovan, I saw that during your SQ, some of the jobs, they actually use more than one node.
Yeah.
Yes. When you compare this, in your table, we don't have that information. Maybe there's something to do with if the run spreads across multiple nodes.
So I wonder whether I did something different when I prepared the table. So a couple of things we can take from here. This is a short example. Probably I would actually look at the longer example because just between 2 runs, it's a bit too short. So I would go for something that takes maybe a couple of minutes, not just a couple of seconds. But I mean, here we don't have so much time. Then I would run the example on this series of what I expected to see is this. I got something different. I think I don't want to now spend too much time investigating. But this is something that can happen. So what I get from here is it doesn't make sense to go beyond 8 cores for this example. It can even be, things can even get worse. And what are possible, if you see something like this, and actually for any example, you will see that there is a certain number of cores nodes where things are not improving, even worsening. And what can be the reasons? Maybe the most typical reason is that at some point, the example, the code spends more time communicating than computing. Those of you who work in larger projects with lots of people maybe recognize the situation that you sometimes feel like, man, I spent half the week in just meetings and writing emails and Slack messages. And this is normal because as the team size grows and as we work in this distributed environment, at some point the communication can take over. And then adding more and more people sometimes doesn't make it go faster. So that's reason number 1. Reason number 2, memory bandwidth. Ole has talked about it, is that we can saturate the memory bandwidth. And here is a Fortran code, which I will not run, but you can try it out. So you can also compile it and run it. And also this is a fantasy code, which are designed to use a lot of memory and not so much CPU. And there is an example on how you can diagnose this. And when you diagnose it, let me zoom in. So when you run this diagnosis on this example code, you can find out that a memory-bound code, okay, it can report that we spent maybe 100% in compute. Maybe we spent no time at all in communication. But then if you see what is really happening at a CPU, it spends almost no time computing. It spends 90% of its time waiting for the data. And also, as Ole said earlier, in this case, it will not help to buy a faster processor, like a higher frequency, because we don't really compute, we just wait for data. And as emphasized earlier, this is also very typical. So it can be communication takes over. As there are more and more cores, there is more and more to communicate and synchronize, like in big projects. Memory bandwidth. There is also the Amdahls Law. And the Amdahls Law, have a look at the wiki page. It means that even if your code is parallel, in your code there are certain portions that are non-parallelized. And as you go to more and more cores, the portions of the code that are not parallelized will start to dominate. So you might also see that. So you will always see that at some point it stops and doesn't make sense to go to higher cores, because then what you are left with the part of the code that is non-parallelized. So as an example, a code where 90% of the code is parallelized, it doesn't make really sense to go beyond like 128 cores. And the communication can be perfect. Everything else can be perfect, but just because then you see the 10% of the code that are non-parallelized, you see them here in the graph. And I have 4 minutes left. Looking at the questions, there is one more thing I wanted to tell you about, and that is, how can you tell? So how can we tell, is this MPI, OpenMP? It's really difficult to tell. So what is MPI, what is OpenMP? We talked about it earlier. But how can you tell whether the code is using one of the two or both? If you wrote the software, you know, because then you've been through it. The problem is that if this is software written by somebody else, it can be really difficult to tell. And I recommend consulting the manual. If they mention any of these things, don't hesitate to contact us or their support of the software. One thing you can do is you can go in the source code and have a look. Is there any mention of MPI or OpenMP in the source code? And I don't know where the stick is here, but I will just show it super quick. I'll show it on this code here. Let's say that I got this code here from the internet, and I want to know. Okay, just a sec. I need to do this. So I'm downloading some code. I want to know, will this understand MPI? Will it understand OpenMP? Still, I recommend go for the documentation, go for the support. And here the documentation is probably very good. But what I sometimes do is I actually grab the code. Git grab MPI. Is there any mention of MPI? Sorry, I should do. Yeah, there is mention of MPI. It mentions some MPI things. Probably this understands MPI. Is there any mention of OpenMP? There is some mention of Pragma, OMP parallel atomic. This is a code that will probably can deal with both. Still, have a look at the documentation. And I have 1 more minute left. Many of us use Python or R or MATLAB. They are often not parallelized, but sometimes they are. So also in Python, you can parallelize with MPI for Python or with multiprocessing. And even if you open up the code and it doesn't mention any of these, it can still be, it can still use shared memory parallelization under the hood. And here's an example, and I don't have time for it, but I recommend you run this example. It's a short Python code that uses NumPy, and all it does, it multiplies two big matrices. And nothing looks like parallel here, but you can use parallelization. And for this, you need to know then that NumPy uses a mathematical library that can be itself parallelized. And what I invite you to do is run this example and run it with this job script, but keep these either commented out or activate these lines. And this is an example that, and compare the timings. And you will see that even a Python code can you make use of course if it uses libraries like NumPy, SciPy, which under the hood then use mathematical libraries. So I invite you to run this example. My time is up. I will catch up with the questions on HackMD. I also understand that what we will try to do at the end of today is to have like a discussion session where we can come back to some of these questions.
Yeah, thank you, Radovan. Yeah, yes, we will come back to this after Marcin's session. So I think we can take a short break. If there is no quick questions now, but you can ask questions on HackMD after the session as well. Yeah, we'll resume at 12:20. Thank you.